All right, we're gonna go ahead and get started here. It's 7 o'clock. So I just have this warm-up problem. So we're gonna give a few more minutes so people can come into the room and you guys can go ahead and get started on this. So what I want you to do is express the integral of 1 over 1 plus x to the 5th dx as a power series. So we kind of talked about this last time. So give it a go. We'll talk about it in a few minutes. We'll do another power series problem, expressing another kind of function. And then we're going to move on to the big stuff today, which is Taylor series expansions. We're not going to get all the way through it, but we're going to get through a good amount of it, and we're going to talk about how to use it in applications and some of the cool consequences behind it. All right. Take a few minutes with this problem, and then we'll talk about it in a little bit. Okay, so let's write this 1 over 1 plus x to the 5th as 1 over 1 minus the quantity minus x to the 5th. And then we can use the power series that we know for this form, right? And just plug it in. So we know that it's normally x to the n, right? So now we're going to plug in what we've got here. So it's negative x to the 5th n, and then we can simplify it, right? So we have the sum from 0 to infinity. So using a geometric, we were able to get this sum here. And recall that we had the quantity r had to be less than 1. So now we've got here that minus x to the 5th is less than 1. Well, this just means that x has to be less than 1. Right? So now we're not quite done because we have to take the integral now. We've got the integral. And we're going to put the power series in here. Ooh, sorry about that. It's x to the 5m. And we've got dx. So that's going to come out to our constant c here, right? And then we're going to have the sum n equals 0 to infinity. Still going to have this alternating nature, so negative 1 to the n. And then we're going to be moving the power up by 1 and dividing by that new power. So we have x to the 5n plus 1 all over 5n plus 1. right? So we actually can find c because we know that this has to be equal to our 1 over 1 plus x to the fifth. And if we do 1 over 1 plus 0 to the fifth, well, this is just 1. And this is going to be equal to c plus the sum n equals 0 to infinity of -1 to the n. And then we're going to plug in 0 here, right? So raise it to the power and then divide. So every term is going to be 0 here. So we're going to have this whole sum is 0. And then that means that c is equal to 1. Now remember that we had that the radius stays the same for integrating. So we still have that r equals 1. Okay, so for number 2, let's try to express arctangent of x. So go ahead, take a minute or two, work on this problem, and then we'll talk about it. All right, so we have arctangent of x. So it might be a little bit of a stretch to imagine that we're still going to be using the geometric here. So if you kind of recall, we have that arctangent of x. This was equal to the integral 1 over 1 plus x squared dx, right? So we've got 1 over 1 plus x squared. This is going to be equal to 1 over 1 minus this negative quantity here. So now we can put this in its power series form pretty easily. This is -1 to the n, x to the 2n, right? So now we've got this power series, and all we need to do is take an integral. So let's keep going. We've got the integral here of now I'm going to insert the power series that we found. -1 to the n, x to the 2n. And this is going to be c plus, we're going to have a power series here, n to infinity, -1 to the n, x to 2n plus 1 over 2n plus 1. So again, we can actually find c. So if we have arctangent of 0, this is equal to 0. And we saw above that when we put 0 into this power series, that it's going to be 0 because we're just adding a bunch of zeros together. And then this is equal to c. So this is actually a pretty cool sum. So notice that this is arctangent, and we have the sum now. C is 0, right? We just have this sum. So let's kind of just write that out. We've got that arctangent of x is equal to and we've got this -1, the n, x to the 2n plus 1 over 2n plus 1. Now, we also remember that from up here, we have that the radius is 1. Because we integrated, the radius is 1. So as long as we're within this interval, we're going to be okay, right? So an interesting sum is if we do arctangent at 1, right? So arctangent of 1, and if you remember, this is pi over 4, right? That means that pi over 4 is equal to the sum from 0 to infinity of -1. And now since we're putting in 1 here and raising it to a power, it's going to be 1 all the time. So we've got this. So first few terms here are going to be, we've got a 1, right, because we've got n being 0. And then, oh, this should be an n right there. So now when n is 1, we're going to have a minus. So let's go ahead and switch that to a minus sign here, right? And then it's going to be 1 over, so now n is 1, so we're going to get 3 on the bottom. Then we're going to get a 1/5, and we're going to get -1/7, and so on. These fractions that we've got here, adding and subtracting them, go to pi over 4, where pi is this irrational number. So I think that's a really interesting sum. It kind of shows that kind of some crazy stuff can come out of these sums, right? Just think about having these, adding and subtracting all these fractions and getting this irrational number. So let's go ahead and go to the next page, and we're going to start talking about Taylor series. So Taylor series are, in my opinion, the coolest subject that we're going to be covering here in Calc 2. So let's do a little plot here. Axes. Ooh, that should have been straight line. There we go. Okay. So let's imagine that we've got sine of x. So something like this is down, back up, right? So if I wanted to approximate this around 0 here, right? Maybe the first thing I would do is approximate it with a linear curve. Well, just good old y equals x So let me try to do a little dotted line here, is a decent approximation around the origin. And if you know anything about small angles, then you know that it behaves like x when x is very small. So if I wanted to do a better approximation, maybe I would use a cubic, right? Because a cubic will do something like this. It'll come up and then maybe back down like this and get spit out somewhere like that. So if we're approximating with polynomials, remember that if we have a finite sum, so we've got some kind of either x or x cubed or x fifth, or even if we're using even ones, that the polynomials are going to blow up at negative infinity and positive infinity, right? So they're going to jump away eventually. So the more you add, maybe the closer you'll hug this function. But eventually, if you have a finite amount, you're going to be blowing out somewhere. So you can probably hug the function for a bit longer if you use more and more sums, so you get more and more accurate. So if maybe you use something like x to the fifth, so it gets spat out around over here. But you can choose these coefficients so that these polynomials fit the curve pretty nicely for some point, and we'll call that a, because we've been talking about a's in these power series. So if we write out what the power series is typically, we have c0 plus c1 x minus a plus c2 x minus a squared. I'm going to do one more term for c3 x minus a cubed, and so on. So if I just plugged in a here, so f of a, all of these terms here, these x minus a's, they'll all go away, and I'll be left with just c0. So that means that c0 is f of a. So I was able to find out what that coefficient is. So what's another way of trying to find out these other coefficients? Well, if I took a derivative here, so f prime of x, I would get c1 plus 2c2 x minus a, and then plus 3c3 x minus a squared, and then so on. Well, if I plugged in a into this derivative, well, again, all those terms will be gone, and I'll be left with c1. So now I've got the term for what c1 should be to fit this polynomial onto some kind of function. Well, you can imagine that if I took a second derivative, f double prime of x, and if you figure it out, you'd get 2c2, and then you would have an x on that one, and you would have 3 times 2c3 x minus a, and so on. So the second derivative at a gives us 2c2. So that's a way of finding c2. And if I did the third derivative and put a into it, I would get this 3 times 2c3. So I could say that the nth derivative at a is going to be n factorial cn. Well, this means that cn is equal to the nth derivative at a divided by n factorial. And if I use these as my coefficients, I can actually define the function like I did from above. But now I actually have my coefficients. So I go from 0 to infinity, and I've got the nth derivative at a over n factorial, and now I've got times this x minus a to the n. And I should have that x minus a, again, is less than some radius. So this is a Taylor series expansion. I can write out functions in terms of their derivatives at a certain point. This a, which corresponds to the center of our power series, luckily enough, right? So a special case of this is when a equals 0, and this is called a Maclaurin series. And that's only when a equals 0. So it's still a Taylor series, it's just a special case. So let's take a look at our first example. So let's find the Taylor series expansion. So find Taylor series. For e to the x centered around a equals 0. So doing what we did above and using our function here, right? See if you can go ahead and find the Taylor series for e to the x, right? And we'll talk about it in just a minute. Okay, so first, let's go ahead and find out what our nth derivative of our function is. So f of x is equal to e to the x, right? Well, our first derivative is e to the x. Our second derivative is e to the x. And that's just going to keep going. So our nth derivative here is e to the x. Well, what happens when we do f of a, which in this case is 0, right? F of 0 is e to the 0, and that's 1. So these are all going to be the same. So we have that fn at 0 is 1, right? So it doesn't depend on n, it's just simply 1. And this is why the power series for the e to the x is so nice. We have e to the x is the sum from n equals 0 to infinity of x to the n over n factorial. And that's it. This is one of the most simplest power series, and it's great. If you keep going in math, you're going to see in a lot of different places. It shows up a lot. So let's go on to our next page here. And we're going to do our next example. We've got number 4. Now find the Taylor series expansion of sine of x, and a is 0. So we're looking at the Maclaurin series for sine of x. All right, we're going to talk about it in just a few minutes. Okay, so we have sine of x and a equals 0. So we have that f of x equals sine of x, and we're going to have that f prime is cosine f double prime is negative sine f triple prime is negative cosine. And then we're going to loop back around, right? So if we look at f of 0, we're going to get 0. Then f prime of 0 is 1. F double prime of 0 is 0. And f triple prime of 0 is negative 1. So what ends up happening here is you've got a pattern of 0, 1, 0, negative 1, and then repeat. So it looks like all the even powers, so we have 0 here, f to the raised to the, it's the 0th derivative, the first derivative, and then the second derivative, we've got 0 again. The 4th derivative is going to be 0, and then the 6th derivative is going to be 0. So what ends up happening there is we get something that looks around, right? So the first term is going to be 0. Then we're going to get this 1 time over 1 factorial, and then an x, right? Because our a is 0. And then the next term is going to look like this. And the term after that is going to be that. And it's going to be some other subtraction, and we're going to keep going. So this is the power series. So instead of writing a coefficient so that I skip every, I make sure that these ones are 0 in between, what I can do is just make my power skip instead, right? So my coefficients are alternating. My powers of x are 2n plus 1, right? Because if n is 0, I get my first power. Then if n is 1, I get a third here, third power. And I get a fifth power. And then these factorials seem to be going 1 factorial, 3 factorial, 5 factorial, just like the powers. So that means that we've got 2n plus 1 factorial. And this is the power series for sine of x. So let's do one more power series, or Taylor series, for natural log of x. And we're not going to have a being 0 because that wouldn't make sense, right? Because we're looking at natural log. So we're going to have a equal 1 here. So go ahead, take about a minute, and then we'll start to talk about the Taylor series expansion for the natural log of x. Okay, so let's write out our derivatives first. We have f of x equals the natural log of x. Now f prime is 1 over x. F double prime is this negative 1 over x squared. Then we've got f triple prime, and that's 2 over x to the third. And let's just do one more. We have fourth derivative as -6 over x to the 4th. Right? So now if we're plugging in 1 to these, f of 1, this guy's going to be 0. F prime of 1 is 1. F double prime of 1 is -1. F triple prime at 1 is 2. And then the 4th derivative at 1 is -6. So other than this first one here, we notice that it looks like it's alternating and that it looks like it's a factorial, which makes sense because we've got this 1 times this -1 that's in here. And then we've got a 1 times a 2. And then this one's a 1 times a 2 times a 3. Right? So we can write out that our nth derivative at 1 is equal to -1 to the n plus 1 n minus 1 factorial. So notice that it's n minus 1 factorial because this seems to be, this is 0 factorial. This is 1 factorial, this is 2 factorial, and then this is 3 factorial. So we're not going to be using this one. So what we're going to do is we're going to skip this index. So normally we start at n equals 0, or we're going to go to n equals 1 first, because this does not follow the expression that we've got here. So we're going to have that natural log of x is equal to the sum. And we're going to start from 1. We're going to go to infinity. And we have -1 to the n plus 1. And then n minus 1 factorial. And remember, this is all over n factorial. And then x minus 1 to the n. So we can actually simplify this a bit with those factorials. So we've got our sum again, from 1 to infinity. And we've got -1 to the n plus 1. And then we're going to have just n on the bottom. And this is x minus 1 to the n. So now this is our Taylor series expansion for the natural log of x. So remember that we've got our function, and we defined it as these coefficients, C1, or C0 plus C1, x minus a, C2, x minus a squared. I'm going to write one more term here, and then we've got C3, x minus a to the third, and so on. What if I wanted to truncate this sum? Because I can't write out an infinite sum and do it by hand. It's impossible. I would be sitting here forever, right? So I might want to truncate this and use it as an approximation. So what if I took up to the squared term? So everything on this side and then I'm going to leave everything on this side out. So I'm going to define this as Tn of x, and I'm going to define these guys over here as Rn of x, right? So that means that f of x is equal to this Tn of x plus Rn of x. And this Tn of x is known as the Taylor series of nth degree, right? So notice that this n corresponds to 2 in this case, right? And the remainder starts at this guy and then goes on, right? So if we have, if Rn goes to 0 as n goes to infinity, then we have that the limit as n goes to infinity of Tn equals f of x. Right? So as n goes to infinity, we're moving this squiggly line further and further down these polynomials. And if this guy goes to 0 as n goes to infinity, then all we have left is f of x equals the infinite sum for these Taylor coefficients, which is good. Right? So there's a way of showing this for specific sums. So we can write this remainder term as f to the n plus 1th derivative at z, and I'll explain what z is in a second. And then we've got n plus 1 factorial. So notice this is the coefficient for the Taylor series expansion. And then, of course, we've got x minus a n plus 1. So a here is where the Taylor series is centered around. And the z is in between a and x. If this is a is less than x, so you could write it x like that if a is larger than x. So that means that this thing is somewhere in, the z is somewhere in between these values. So we can't really lock down what this is, but most of the time what you can do is bound it. So that brings us to our next example. Let's look at this value for sine of x. And what can we find out about it? Right? So go ahead and think about it, do some work on it for about a minute, and then we're going to talk about it. All right, so this remainder for sine of x. Well, we know that our remainder here, and I forgot to mention that we've got the Maclaurin series. So this is just basically example 4, and what's the remainder for this if we were to truncate it, right? So we've got this coefficient, and now because a is 0, we've got x to the n plus 1. Now, what can we find out about this? What is, so the nth derivative of sine here, or the nth plus 1 derivative, is going back and forth between this sine or cosine, right? And if a is 0 here, then we either have 0, we either have 1, or we either have negative 1. So what we can do is bound this, right? So we know that this has to be true, right? It's definitely 0 or greater if we take an absolute value. And we also know what this is equal to. We can take the absolute value of the n plus 1 derivative at z, and then the denominator here is always positive, so it doesn't need absolute values. And then we've got the absolute value of x n plus 1. Now, this can also be bounded, right? Because if there's sines and cosines, the most that this term can be here is going to be 1, right? So that means that we can bound this by the absolute value of x n plus 1, and then we're going to have n plus 1 factorial here in the bottom. So if this is bounded below and above here, then it might start to look like something like squeeze theorem. So what is the limit as n goes to infinity of this absolute value of x to the n plus 1 and then n plus 1 factorial? This limit is 0. Factorial grows way more rapidly than any power would. So with this being true, then we've squeezed this Rn here. So that means that we know that the limit as n goes to infinity of the absolute value of Rn of x, this is equal to 0. And because it didn't really matter what x was going to be, it means that x, this Taylor series expansion, is good for all x. So normally we had some kind of radius, or radius is in infinity for sine of x. Right? Okay. So let's go to our next page here. And this leads us to our last example. Let's compute the integral of e to the negative x squared dx. So go ahead and take a minute to think about how you would integrate this with all the techniques that we might have learned before. And then think about how we might be able to use what we've just learned with power series and Taylor series expansions to find out what this integral is. And then we're going to talk about it in just a minute. Okay. So we have this integral of e to the negative x squared. And e to the negative x squared is actually, it has a special name. It's called a Gaussian. And it looks like, do a quick sketch. It comes up like this and comes down like that. It's used a lot in probabilities, and it actually shows up in a lot of different places. A lot of, in like, for instance, it shows up in quantum mechanics, shows up in like grade distributions and statistics a lot. So it's a very important function. And now we're trying to take this integral of it. And if you look back and try to apply some of the integral techniques that we've learned previously in Calc 1 and Calc 2, you're not going to be able to solve this integral. So it's kind of a trick question to see if you could figure it out. Let me know if you actually could figure it out. I would be really impressed. So how do we use power series and Taylor series expansions to help us with this? Well, we can find the Taylor series expansion for the integrand, this e to the negative x squared, this Gaussian curve. And then we can take the integral, like how we learned to take the integral of power series, because Taylor series is a power series, to give us some insight into what the power series of this integral looks like. So we can probably take a few terms and do a good approximation of what this integral is. So let's start with e to the negative x squared. Now, you'll probably start by taking the derivatives of this guy and then maybe centering around 0, do your approximations. But notice that this is very close to, well, it is an exponential, right? So if we just have e to the x, right, we just had e to the x, and you recall that the power series for this was pretty simple, right? It was just x to the n over n factorial. Well, if we put in this negative x squared into here, we'll actually get the power series for e to the negative x squared. This is also nice because the power series for the exponential e to the x has a radius of infinity, so it converges for any x. So now we've got -1, the n, x to the 2n over n factorial. And if we want to know what this integral is, so we have the integral of e to the negative x squared dx. We can just take the integral of the power series. This is -1, the n, x to the 2n over n factorial dx. So we've got c here. And we're going from 0 to infinity. And we're still going to be alternating. And our exponent goes up by 1. And we're still going to have that n factorial. And then we're going to divide by our new exponent. And this is what we have for the power series of this integral. So if we wanted to approximate what this integral is, if we've got bounds, then we would have bounds on here, and that means we could put bounds on this and then do the sum and look at the first few terms, and then we're able to approximate what this guy might be, right? So if we keep on doing more and more terms, we'll get this more and more accurate, right? But to have it in a form that's not a power series and indefinite takes a lot more math ability. So maybe someday you'll get there and you can look back and be like, oh, instead of doing a power series, we'll just do this. But for now, this is one of the good applications for power series. And likewise, you can use it with derivatives. You can use it with even limits. So maybe next time we'll do an example with some limits. But we think we're running out of time. So we'll probably start off the recitation on Wednesday with a Taylor series application for limits and maybe a derivative. And then we're going to be talking about some multiplicating and dividing power series by one another. So I hope I've answered any questions that you guys might have had. If you have any questions, just shoot them in the chat. We only have a few minutes left. If we don't have any time to cover all of the questions, then you can shoot me an email. Otherwise, I'm pretty much done. I'm going to end the recording and see if you guys have any questions.